Thank you very much, Bruno. I did not know you knew all that of my career, but it's always a pleasure to see you. Okay, so I hope you hear me all. I'm honored to have this opportunity to present you one courses I used to give in the University of Burgundy, and I have added some slides to illustrate the issue of sustainability of plant fiber composites. So I have around more than 60 slides, and I think it will take less than an hour. So composite materials are widely used now, and they have applications in almost of industry fields, areas. In these slides, I try to illustrate where you have the use of composite materials in defense industry, space, also in motorsports, which is quite new. And in automotive industry, you have more and more use of composite materials. As example of the use of composite, you see application with Renault Scenic car regarding the rear door of the Air Force Scenic. For example, inside the car, you have a Citroën that has developed some parts which are made of short glass fibers impregnated with polypropylene or polyamide. And this, the left image on the upper row is the frame of Alfa Romeo C4, which is made fully in carbon. So more and more you have the use of composite materials in automobile industry, and it's now around more than 20% of the global weight of the vehicle. And you have illustration of the parts in which you have composite parts. So if you look in aeronautics, the image I have was from 2010. The Airbus model, a point here, has more than around 53% of composite in weight. Also, for naval or maritime industry, you have the use of glass fibers and more carbon fibers. So why are we interested in plant fibers? So we need to find sustainable replacements of the man-made fibers, namely glass or carbon or aramid fibers, used in the reinforcement of composites. And that need has drove to start using sustainable natural fibers. So let's compare some man-made fibers to the most used plant fiber in Europe, let's say flax. If we look at the Young's modulus, we can see that the carbon T300 has a high modulus compared to glass and compared to flax, which among the three has the smallest modulus. But this modulus must be faced to the density. And when we look at these three materials, we see that glass, e-glass, which is the most used material, is the heaviest. And flax, which had the smallest modulus, has the density, the smallest density. So the mechanical properties are to be compared or divided by the density to have the specific value. And when we do that exercise, we see that the plant fiber, flax, starts being competitive. In addition, we can look at the price, and the carbon is the most resistant, but at the same time, the most expensive. And we see that the plant fiber is the cheapest. And also we can focus on the energy or the carbon footprint of this material. And we see that the plant fiber has the smallest footprint among these materials. So let's summarize some points. 90% in weight of the reinforcements used are made of glass fibers. The emission of pollutants during the processing is important, and there is no viable reprocessing industry for the man-made fibers after use. The plant fibers present the advantage to be biodegradable and are provided from renewable resource. And natural fiber composites are lighter, as we said, regarding the density, and that gives them interesting specific properties. Just to illustrate what I'm saying, in the left chart bar, you have in blue the modulus, the strength, and the maximum elongation strain of glass fibers compared to the properties of flax fibers, divided by the density, which is of 1.5 for flax and 2.6 for glass. We see that the specific modulus or strength of flax starts being interesting because it is superior to the specific properties of glass. Some illustration of natural fiber composites applications in automotive. You have they are used now in all areas of our life, but I have focused on automotive applications. Example of spare box for Mercedes-Benz door panel made of jute fibers. For the motorsport, you have the back seat, the seat of Formula One, or the rear shift of some Peugeot models, and the battery holder of Peugeot models also. So this means that these natural fiber composites are used now, and the first attempt to use them was done by Henry Ford in the 1940s, where he created some parts of the automobile with hemp fibers. So in this slide, you can see the history of the use of natural fiber composites in automotive. And you see that it started around the 30s, 40s in the 19th century. And you see a long line illustrating the different steps and the improvements using natural fiber composites. You can find this graph in the book El Zaifi, Manufacturing Automotive Component for Sustainable Natural Fiber, Springer 2021. So in this presentation, I will try to review the natural fibers and to illustrate the issues regarding their sustainability in the fatigue behavior and their resistance to impact loading. Sorry for this remaining line. Okay. So the natural fibers are derived from natural sources, which may be more environmentally friendly than equivalent systems based on synthetic fibers impregnated in petrosourced resins. Natural fiber composites are regarded as greener alternative materials to replace already existing composites in different market sectors. So the objective of sustainable composite is to promote the use of materials having high performance and sustainability that are provided from renewable resources, that have low environmental impact, and end-of-life solution. So at the same time, so this is the development of Christophe Ballet in 2022, in 2012. What are the interests of natural fibers? As we said, they are renewable, sustainable, they are recyclable, and some of them, depending on the matrix with which they were mixed, can be biocompostable at the end of life. They reduce the environmental impact, and they can reduce the impact on human health. So here we have to be careful. It does not mean that because they are natural fibers, they are safe for human, but it can be an issue to try to make them safer instead of, for example, greenhouse gases produced in the processing of man-made fibers. And also they have lower cost production, and we can say that the finishing of parts gives them attractive, can give them attractivity. That is the ability to maintain a natural finish when materials are made with natural fiber composites. So the composite reinforcements mainly are mineral. We know glass fibers, carbon fibers, for example, basalt fibers. And on the other hand, we have organic fibers that can be synthetic, artificial. Within them, we can see we can notice the aramid fibers, boron fibers, and in green you have, in the green cell, you have natural fibers, which have two origins: animal fibers and plant fibers. So in this slide, the animal fibers can have three origins. They can provide from wool, for example, coming from sheep. They can provide from hairs of animals, for example, alpaca. They can provide from secretions of animal, for example, silk. And at the left side, we have the mineral materials, for example, asbestos, which now more and more forbidden. In the middle, you have the plant fibers that can be agricultural, that means that obtained from seeds, or that can be woody materials. So the natural fiber used for composite reinforcement usually are coming from seeds, stems, leaves, or can provide from fruits or from bast fibers. Examples are given below that we know: cotton fibers, kapok fibers, bamboo fibers coming from the stem. From the leaves, you have the sisal, banana fibers, palm fibers, coir fibers provided from coconut tree. And the bast fibers, as an example, we can see the flax, the hemp, also mescanthus, jute, canaf, etc. So let's illustrate some natural fibers. First, the animal fibers that can be wool from sheep, that can be from hairs like alpaca, that can be silk, that can be spider web or feather from birds. As for plant fibers, they can provide from cotton, from kapok, if it is seeds. From the stems, you have bamboo, the wheat straw or rice straw, mainly for insulation use, and they can provide from leaves, sisal, banana, and from fruits, example, coir fibers. Natural plant fibers or vegetable fibers have mainly three constituents, which are cellulose, hemicellulose, and lignin. The differences between vegetable fibers depend on their chemical composition, their physical properties and also their mechanical properties. So the common vegetable fibers shown here are provided from the bast, the leaves or fruits, and mostly you have flax, hemp, kenaf, jute, of sisal, abaca, pineapple fibers, or coir fibers. Natural fiber composites are mostly used in automotive industry or in insulation. So in the plot here, we see that around 71% of the use of natural fiber is in automotive industry, and you have 13% which is around insulation, and we have sporting and electronic use. When we look at the distribution of the production of vegetable fibers, we see that the jute is the most produced reinforcement. You have also coir, you have also flax, and in limited quantities, you have hemp, kenaf, etc. So when we look at the natural fibers that are used in automotive industry, we see that flax is the most used, even if it is not the most produced fiber in the world. And it is followed by kenaf, by hemp, jute, coir, abaca, and sisal fibers. In the world, you have the greater producer of fibers that are Bangladesh, in Asia, India also, France, namely with flax fibers, and Vietnam. So the trend in the use of natural fiber is increasing since the 60s in the 19th century. So what are the parameters that can be influencing in the properties of plant fibers? They can be cultural parameters, that is the variety of seed, that can depend on the soil in which the seeds are sown, that can depend on the phytosanitary treatments, it can depend on the fertilizers, and the time at which the plant is used, that means its maturity. Parameters can depend on the season, on the temperature, and on the forecast. And also, they can have the influence of the process, that means during the drying, during the wetting, the scotching, the spinning, or during the mechanical or chemical treatments the fiber has faced. So let's look at the mechanical properties of the natural fiber reinforcement. So when you look at the Young's modulus, we see that their modulus are quite low compared to synthetic fibers, which are mostly used in, for example, automotive or iron industry. So we can jump to the strength. We see that the fiber provided from the stems like flax, kenaf, hemp have important strength, but it is still smaller than the properties you have in when you look at e-glass, air glass, carbon fibers. So let's now look at the density. Overall, plant fibers have a density of 1.5, while glass fibers is the heaviest. It is around 2.6, and we have carbon around 1.8. So why are these three properties important? Because they permit us to look at the specific properties. So in this plot, you have in the axis the modulus divided by the density, and in the y-axis you have the strength divided by density. So you can see that carbon is one of the more rigid and resistant material as for Kevlar and glass. So let's look at the position of natural fibers. Here you have flax, hemp, kenaf, which are below glass fibers in strength, but they have better specific modulus than glass. And under these three fibers, you have a cloud of other fibers that can be silk, that can be scissor, coir, pineapple, or cotton fibers. So in the next slide, I will focus on the hemp and flax fibers, which can be competitive fibers compared to e-glass, which is the main reinforcement used. So, as you know, France is the first producer of flax in the world. So here we see the image of a flax field, which is flowering. So it's a yearly plant. It is sown in early spring, around March, and it gives fibers and oleaginous seeds. So we have 4 steps, which are the emergence, the rising of the plant. It takes around 45 to 60 days. And for example, around April or May, the stem lengthens rapidly and the stem reaches 1 meter of height. The growth stops at the beginning of the summer as the flowering progresses. The next steps are the flowering, which lasts around 15 to 25 days. It is a long fiber that has several tens of centimeters, important height compared to short fibers from cotton or hemp, and medium fibers that can be from wool. Its characteristics are the lightness, the rigidity, and the resistance. On the back and left side, you have images of flax field where the flax has reached maturity and was cut for processing into fiber. So the harvesting usually is grubbing around July or June, end of June. After that, the next process is the retting. That means that it is the isolation of the fibers by degradation of the stems attacked by microorganisms that can be done by water, by air, or by enzyme. The role of the enzyme is to digest the pectins, which binds the fibers together. So the cutting is the beating and the crushing of stems to obtain technique fibers. So it is done for flax and hemp, and it separates the woody parts of the fiber. Usually, hammer mill and fluted cylinders are used. The following step is the cleaning, that means the removal of the locks, and then the carding. It is the alignment of the fibers by brushing and combing. After that, we have the spinning, that means the bonding of fibers by twisting, obtain yarns or filaments. And this lastly can be waved, braided, or knitted to have the fabrics. So when we look at the flax fiber or the flax plant at different scales, we see that the stem has we can see that the stem has a diameter of around 3 millimeters. The stem can be divided into bundles, and these bundles are aggregates of fibers. So when we look at the fiber, we are at the micro scale. We see that the fiber is made of cell walls. We can distinguish the primary wall, secondary wall, up to 4 walls. And in the middle of the fiber, we have a hole which is called the lumen. So when you look at the walls, you can see it's made of microfibers that are banded by pectin. So the walls are made of cellulose microfibers that are composite layers. The microfibers are banded by pectin matrix. The microfibers are slightly inclined. You can see here an angle around of 10 degrees, and the interface between 2 layers is made of hemicellulose. So when we look at the flax fiber in SAM here, we see that its cross section is quite polygonal, not elliptical, not cylindrical, but it has faces and can be compared to a polygonal material. So let's compare the cross section of flax fiber to glass fiber, which is man-made fiber. We see that the flax fiber has some default along its length, while the glass fiber is straight, has good cylindrical and perfect geometry. Here in the bottom pictures, you can see the cross section of flax fiber, and in the left side of glass fibers, you can see the perfect cylindrical circular cross section of the glass fiber and the polygonal cross section of the flax fiber. And in the middle, we have some black strands which correspond to the emptiness, the hole, which was the lumen identified in the middle of the flax fiber. So this means that when we test the properties, namely the mechanical properties, we have a variation about of 20 to 60% for the flax fiber, and around 3 to 13% for the glass fiber. Sorry for the commentary, which was not in French. So there is no unique variety or species of flax. Namely, here you have around 8 varieties, and among them, the one which is called the harvest is the one that has the highest mechanical properties. And this variety is the one which is used mostly as natural fiber reinforcement for composite applications. So now let's compare, let's pull on the flax fibers and compare its behavior, their behavior to the one of glass fiber. We see that the scattering of the flax fiber is quite important. The scattering in maximum stress, that is the strength, and the scattering also in the maximum strain. Compared to the glass fiber behavior, it appears that the glass fiber has, it seems like a bundle of flux, and you have at the origin the same properties. You have a scattering in the strength and in the strain of glass, but this scattering is less important than the one we have noticed in the left images for glass, for flax fibers. Some authors have tested the properties, that means the Young's modulus, the strength and the maximum strain of flax fibers uniquely. It is what was done by Ballet. Some tutor has looked at the variability of the flax fibers, but by mixing different properties, different varieties, sorry. Charlet has mixed varieties and localizations along the fiber stem, along the flax stem, and we can see that the scattering that illustrated by the coefficient of variation, which is the standard deviation divided by the average value, is quite important, and it can reach for the modulus around 60%. That means that asks the questions of the reliability of the use of these fibers, but we'll talk about it in the coming slides. So when we divide the stem of flax in 3 parts, that was as Charlet did it. So we can notice that there are bottom fibers, which were the oldest in the stem because they were the first fibers. We have the middle fibers that developed during the rapid growth and represent the longest fibers. And we have the top fibers whose growth was interrupted early because of the harvesting. So it appeared in the test that the middle fibers, which benefited from good climate during their growth, have better mechanical properties. This can be seen in the pictures here. So the average fibers, the middle fibers, have the highest Young's modulus, or the highest strength, or the highest ultimate strength, as their diameter is small, and that means that it is preferable to use these fibers when we want to optimize the mechanical properties of the flax fibers obtained from the flax plants. So now let's look at the properties of hemp plants, which has the scientific name of Cannabis sativa. So it's a green plant. In the bottom pictures, you see trees of hemp, and you see that the hemps are harvested during the summer. Here you have, cross sections of hemp stalks. It is the stems that were cut, and in the middle of the plant you have a hole, and you have the fibers inside the wall of the plant. Among the plant fibers, one of the important advantage of hemp plant is that it requires no fertilizer in its growth, no herbicide and no pesticides. So that makes it, among plant fibers, the most sustainable of them. We can notice also that under normal weather conditions, it can reach 4 meters within 3 months. Many of its byproducts can be valorized, namely the fibers, which represent around 30% of the weight, the shanvat, the powder, and the seeds also. Hemp has acoustic and thermal insulation properties that are good. It is rot-proof, fungicidal, and not attacked by rodents and insects. And it does not need herbicide to grow. So it is widely used as reinforcement with thermoplastic matrix because of its thermal stability. As a disadvantage, some varieties of hemp have psychotropic properties, which implies some legal aspects. So in this slide, lastly, I present illustration of the use of jute fabrics, which is one of the most used natural fiber reinforcement. So this slide summarizes the known mechanical properties of plant fibers. We can see that the most used are those who have the highest mechanical properties, namely the tensile strength, the Young's modulus, and their low density compared to glass fiber gives them important advantage. So in front of the natural fibers, you have the use of biopolymer. Because we cannot talk about biocomposites when only one constituent is issued from plants. It could be interesting to focus on the bio-based matrix. Some of them have thermoplastic properties, which make them recyclable. Some of them have thermoset properties, which gives them good mechanical properties, but limits the possibility of retreatment at the end of life of the parts. So both thermoplastic and thermoset matrices are being used with natural fibers. Polyamides, polyester, and polycarbonates are not used for natural fibers because they require more than 250 degrees during the processing. The natural fibers have, in general, low thermal stability, which limits the processing temperature of polymers below 230 degrees. That's why the most common used thermoplastic matrix is the polypropylene, whose melting temperature is around 120 to 180 degrees. Thermoplastics will help in producing recyclable composites, unlike thermosets, and the thermoplastics are of high interest in the automotive industry due to their short production cycle time, and there is no need of post-curing to optimize the properties. The processing of thermoset matrix is much easier, however, than the processing of thermoplastics, which usually are solids, and while thermosets are liquids. So in this plot, we can distinguish three types of bioplastics: those who are bio-based but non-degradable, those who are biodegradable but fossil-based, and those who, to my opinion, should be developed, the bio-based one, and the having biodegradable properties. That is, the carbon footprint of bioplastics is low, and this will reduce the overall carbon footprint and the greenhouse gas emissions of the final composites. So now, what are the challenges in the development of natural fiber composites? First of them is to improve the fiber extraction techniques. Second point is to improve the adhesion, the bonding between the fiber and the matrix at their interface. Some studies recommend the use of coupling agents or mechanical treatments to improve the bonding between fiber and matrix. One challenge could be their long-term life. That means the behavior to moisture absorption, the fire smoke resistance, and the resistance to bacteriological attacks. That means the sterilizations to avoid biodeterioration. Also, it could be interesting to improve the reduction of life cycle of environmental impacts. That's the life cycle assessment, the impacts on human health, and there is a philosophical questions, which is, would we improve the development of natural fiber for composite or industrial applications, forgetting the importance of foods, knowing that the soils have limited possibilities for the culture of the plant fibers. And lastly, we can name the sustainability, which in mechanics of materials covers the ability of materials to have long-term performance. That means the resistance to impact, to endurance by fatigue loading or aging. So in the following slides, I will present two studies regarding the fatigue and the impacted behavior. But why do we use the natural, or why do we develop the natural fiber composites? We try to develop them because we need to handle their processing, to know how to test them better, and to analyze the test results with all the satisfactory parameters. This will help to build models. These models must be compared to the test results, and these models must present some robustness. And within these conditions, the natural fiber composites will be transferred for industrial applications. So the applications I present are at the scale of the composite laminates, not the scale of the seed or the stem of the fiber, but we suppose that the properties of the fiber are known and the fibers were processed into continuous reinforcement mixed with a petrosourced, which is not biopolymer, petrosourced matrix, and to have laminate composites. So we have results on the quasi-static properties, their fatigue properties, and their tolerance to impact. So the Flax fiber is made of different cylinders, and within these cylinders, one is named S2 cylinder by Ballet, and it is the thicker cylinder and has the orientation of fibers of around 10 degrees. We'll see that this cylinder has important influence in the long-term behavior of the flax fibers. The process is an important issue because you can see that if the carding is not satisfactory, some fibers can have cortex surrounding them, and this will first have no good mechanical properties, and secondly, diminishes the bonding between the fiber and the matrix. So these fibers were processed into fabrics, unidirectional fabrics. balanced fabrics 090, stitched with threads, usually cotton threads, spaced with around 10 millimeters. So the fabrication process was thermocompression process with two heated press, and within them you have the composite layers, which are flax fibers mixed of polymeric matrix and the control system. So the curing cycle is combining the pressure, which for flax is a maximum of 7 bar. The temperature is 60 degrees during 8 hours, and the results are compared to the properties of glass fiber reinforced epoxy composites. So for the glass, we have a pressure of around 2 bars. Why this difference of pressure is to have the comparable fiber volume fraction. So once the laminate of flax was processed, you see the plate of around 250 millimeters surrounded by an excess of matrix. The plate was cut and instrumented with aluminum taps regarding the ISO standard. And then we can see the properties of flax epoxy 090 composite and glass epoxy 090 composites. We see the layup here, and we have a volume fraction of around 42%. When we look at the microstructure, we can see the flax epoxy does not present straight layers due to the pressure of 7 bars, and the glass one has more straight layers in its microstructure, but has more important volume fraction. We can see the porosity of the black pixels here, and which were estimated by image treatment to around 6% for the glass epoxy composite and around 3.1% for the flax epoxy composites. So the specimens were tested in quasi-static loading, which refer to the ISO standards. Specimens have length of around 250 millimeters with a gauge length of around 1.50 millimeters. Sorry. I have jumped to the end. Let me go to the right slide. We were here. This slide. Okay. So these are the different types of specimens: tension specimens, compression specimens, and implant shear specimens that were tested in quasi-static test with temperature control at around 23 degrees Celsius. So when we plot the tensile curve of flax epoxy specimen, a UD1 of 12 layers, we see a straight behavior, but this straight behavior presents two slopes at around 0.3% of strain. This bilinearity is typical of plant fibers and is due to changes inside the microstructure of fibers. This bilinearity is persistent even if the number of tests is increased, and causes some trouble for the measurement of the Young's modulus, which is set in the ISO standard in this range, which is measured according to the ID standard in the range of the change of slope. So that means that the modulus of the composite reinforced with Flax measured is a mix of the first slope and the second slope, if we refer to the range given by the standard. So when we look at the morphology of the specimens after the test, we can see some damages, which are the fiber breakage, and at the interface of the matrix and the fiber, we can see some debonding. We can see some debonding here. When it's a Flax epoxy, 90-degree oriented fibers, we can see after breakage the places where the fibers were, and we have some remainings of fiber, which means that there is some peeling, and which explains that the adhesion, the bonding between the fiber and the matrix is quite low. So let's compare the properties of intention of glass epoxy 090 fibers and Flax epoxy 090-degree oriented fibers. So we see that the glass in blue have higher modulus, higher strength, and higher maximum strain. In in-plant shear also, we have the glass which presents more important properties in the shear modulus, the shear strength, and the shear strain. Also, in compression, the difference is the more important. This can be divided by the density to compare the specific properties. The smaller density of the Flax epoxy composite, which is 1.28, compared to the glass epoxy composite, which is 1.73, diminishes the difference between the results we had of glass epoxy compared to Flax epoxy. But it appears overall that glass has better property, glass composite has better properties than Flax epoxy composites. We see the in-plant shear, where the fibers are oriented at ±45 degrees, we see that the specific resistance in shear of the Flax epoxy is around 3% higher than the one of glass epoxy composites. The important difference we have in compressive properties can be linked to the fact that the Flax epoxy are not straight when they are processed, and the lack of geometry causes the rapid instability in compression that diminishes the compressive properties of the Flax epoxy composite in compression. We can see in these images that the layers, for example, here we have the 0-degree layer of Flax, and here we have the 90-degree layer of Flax are inside the composite, not straight. That means that when they are loaded in compression, their properties decrease very rapidly. So let's look at the variability of the Flax UD composite. We said that the elementary fiber has variability of its properties around 63%, around 60%. But we see that when the laminates of Flax are processed, we have a tendency of an averaging effect of the properties, except the Poisson's ratio, the in-plant Poisson's ratio, which is around, which has a coefficient of variability of 19%, and the compression strength in the fiber direction. Apart the Poisson's ratio and the ultimate compression strength, we see that the overall properties of the Flax unidirectional are lower than 5% compared to the properties of the elementary fiber, confirming the averaging effect. So when we compare now the properties of the Flax epoxy to the glass epoxy composites, we see that the Flax epoxy are brown here, the glass epoxy are plotted in blue bars. We can see an overall average value lower than 10%. So what does it mean? That means that the level of reliability of the Flax epoxy composite is comparable to the one we have for glass epoxy composites, even if elementary glass fibers have a coefficient of variation of around 13%, as we have seen. So we can note that the Flax epoxy composites have bilinear behavior. Their mechanical properties are lower than that of glass epoxy composites, but due to the lightness of the Flax epoxy, the difference becomes small when these mechanical properties are divided by the density. And we can see that the reliability, that means the overall variability of Flax epoxy composites, is at the same level of the glass epoxy composites. Sorry for the French in this slide. So next study that was done is the fatigue behavior of these composites. It was sinusoidal loading with a ratio of 0.1. The frequency was around 5 hertz, The temperature was regulated to 22 degrees, and the loading levels were between 80% of the ultimate tensile strength to 40% of the ultimate tensile strength. And at each level, 3 to 12 specimens were tested. The target was to reach 2 million cycles before stopping the test. So we can see that that flax fiber composites have stable behavior and have a small self-heating during the fatigue loading, and the ISO-based specimen has regular heating during the fatigue loading. So the test shows clouds of points, and the test was stopped at 2 million cycles. The higher points correspond to 80% of the ultimate tensile strength. The lower correspond to 40% of the ultimate tensile strength. So once these points, these life cycles were obtained depending on the loading stress, we can plot the Wöhler curve, which the average one, which corresponds to the 50% of probability of life of the specimens. And we can make the result more confident by increasing the probability level to 80 to 98% of probability of failure of this specimen in tensile loading fatigue. So the tensile loading results can be compared to glass ones, which are plotted in blue, knowing that the flats are lower here in red. So we see that the long-term behavior of Flax is quite lower than that of glass when we approach the millions of cycles. When we look at the shear behavior, we can see that around the million of cycle, we have Flax epoxy composites that have better behavior than glass epoxy composites. So these properties can be divided by the density, and we can see that the specific life cycle of the Flax epoxy composite is comparable to the specific life cycle of glass epoxy composites. That means that if we have to produce long-term parts composites, making them in Flax reinforcement will be equivalent to making them in glass when these parts are to live more than millions of cycles. And when we look at the shear long life behavior, we see that the Flax has better behavior than glass here. So let's look at the distribution of the life cycle of the specimens at each loading level. We can see that the distribution is normal, quite Gaussian, depending on the loading level. So the left curve is the one at 80% of the ultimate tensile strength, and the distribution of at 40% of the ultimate tensile strength. We can see also that as the Flax fiber composites are loaded, their variability, the scattering is diminished. And the more you load the glass epoxy composite, their scattering increases. this is favorable to the Flax epoxy composites. That means that within the time and within the increase of the loading cycles, the scattering is diminishing, and we have a better prediction of the behavior of the Flax epoxy composites. So now, sorry, let me remove this picture. So now let's look at the hysteresis loops, which means that the combination of the loading and the unloading paths during the fatigue loading. So the shift we have between the stress and the strain means that we have some dissipated energy, which is inside the ellipse we have here. So it is interesting to focus on 4 parameters during the fatigue loading, which are the secant modulus, the plastic strain, the fatigue modulus, and the size of the hysteresis loop, which corresponds to the energy dissipated throughout the cycle. As we can see here in the left picture, we see that, for example, for the glass, the slope of the hysteresis loop is diminishing from the beginning to the last cycle. And when we focus on the glass Flax epoxy composite, the contrary is noted, is that at the end of life of the Flax epoxy composite, you have an increase of the slope of the hysteresis loop, which corresponds to the secant modulus. So let's look at the residual strain. We can see that the residual strain increases as much as the loading level is increased. And the fatigue modulus, which is the slope starting from 0 strain and 0 stress to the top of the hysteresis loops, it decreases throughout the life of the specimen, but is increased depending on the loading level. So when we look at the size of the hysteresis loops, which is the energy dissipated, we can see that as much as the loading level is important, you have the importance of the energy dissipated. But throughout the life of the Flax epoxy composite, we can see that the size of the hysteresis loops is diminishing. In the early cycles, you have higher, more important energy enclosed in the hysteresis loops than in the end of life. What differs for glass epoxy 090 composite, we can see that the size of the hysteresis loop is quite small at the beginning and increases. That means that the glass epoxy dissipates more energy at its end of life than the Flax epoxy, which have a kind of self-healing during its fatigue loading. So when you look at the secant modulus, which has the same trend than the dissipated energy, we can see that as in the axis, x-axis, you have the number of cycles divided by the total cycle. So when we are at 1, that means that the specimen has broken. And at 0, we are at the early loadings. We can see that there is an increase of around 7% during the loading of the Flax epoxy composites. When they are loaded at 0.90, we see that increase of the modulus. At the contrary, when we compare it to glass here, we can see as much as they are loaded, we see a decrease of the second modulus. At plus minus 45 degrees, for both type of specimens, the second modulus diminishes. So this is an interesting result. That means that natural fiber, or let's say Flax epoxy composites, when they are loaded, they have an increase of their rigidity, which is linked to the fact that the microfibrils that are in the wall, the cylinder, namely the S2 cylinder wall, inclined to 10 degrees, or depending on the number of cycles, are tending to align along the loading axis, so to go to 0 degree. So, and when you look at the increase of the number of cycles, there is a realignment of the microfibrils, which gives an increase of the rigidity during the fatigue loading. We saw for glass epoxy composite, the more they are loaded, the more the hysteresis loop increases, and the more the slope of the hysteresis loop diminishes. So we can note that the fatigue behavior of Flax epoxy composite is comparable to the behavior of glass epoxy one. The volar curves of Flax epoxy are lower than the volar curves of glass epoxy. But for plus minus 45 oriented fibers, Flax epoxy presents better specific fatigue behavior than glass epoxy fiber. We have seen that there is an increase of the rigidity of Flax epoxy that can reach 7% when all fibers are along the loading axis, and it can be around 2% when it's a laminate of 0.90 degree fibers. The decrease of the increase of rigidity is attributable to the fact that in the 0.90 composite, you have half of the composites of the fibers that are perpendicular to that oriented perpendicular to the loading axis, and in this direction you have important development of damages, and you have also the increase of the density of cracks inside the composite. So let's test Flax epoxy composites in impact. The laminates that were chosen were quasi-isotropic layers. It was the same layer, but when we look at the outer orientation, one was parallel to what was called the x-axis, and the second was perpendicular to the x-axis. This change of positioning makes that the membrane rigidity to be the same for the two specimens, but the bending behavior differs because of the positioning of the outer layer of around 20%. These two types of specimens were impacted. Sorry for this. These two types of composite were impacted on a 3-point bending setup, but the impactor was raised at the height of maximum 2 meters, corresponding to an incident energy of 10 joules and a maximum speed of 3 meters per second. The nose of the impactor was cylindrical with a diameter of 16 millimeters, and specimens had width of 94 millimeters and 142 millimeters, as you can see in the picture. And the span was around 100 millimeters. So after the impact, we can eliminate the noise by Fourier transformation, and we have the evolution of the force depending on the time, and the impact duration is around 15 milliseconds. So when the impact has low speed and low incident energy, you have the loading path, which differs from the unloading path, and the area inside the loading and unloading representing the dissipated energy, which is quite small at small impacting energy. So when you increase the incident energy, the duration time of the impact is increased, and also the maximum force is increased. At the same time, you have an increase of the dissipated energy, which creates damage inside the specimen. So when the damage is created, we see irregular evolution of force depending on time, and we can see that the loading unloading curve show important dissipated energy. So here are plotted the evolution of the energy dissipated as a function of the impact energy. We see that it's increasing. We see that the deflection in the lower face of the composite during the impact is increasing depending on the incident energy. We see that the duration also of the contact between the impactor and the target is increased as the loading force is increased also during the test. So the deflection of the specimens has been measured during after the test, and then we can see that when the impact energy is small, there is no deflection at the outer plane of the specimen. And when the impact energy is of the maximum of 10 joules, we see important deflections, which is more important than the thickness of the plate. So at low impact energy, this is the backside face, no crack is visible. And when we have cuts at the middle of the impact point, we can see some beginning cracks at the middle of the specimen. So at around 4 joules at the backside face, you can see some whitening crack, which was called the barrier visible damage, and an increase of the cracks, not only at the interface of layers, but inside the layers also. When we have impact at 6 joules, we can see important whitening and crack in the backside of the specimen. And we see that the increase of cracks, the crack density is increasing around 10 joules, which was the maximum energy. Important cracking happened, and the outer layer in the backside face presented important cracking. So in blue, you have the loading unloading pass during the impact, which was compared to the loading unloading curve of quasi-static bending of the plates. So this plot shows that there is no dynamic effect in the behavior at the speeds and the energy of impact. And we see that the trends in the crack length in the backside face as a function of the impact energy are the same for the specimens with outer layer at 0 degree, the blue one, and specimens with outer layer at 90 degrees. So there were in that study no important differences. We saw that those who were called quasi-isotropic 0, which has the outer layer at 0 degree, had higher maximum forces during the impact than specimens with 90 degree oriented outer layer ones. So the peak forces has been recorded, the duration contact, and also the dissipated energy. So the black plot seems to be equal energy plot. The fact that these plots are below the black lines implies that there is some dissipated energy, but not significant difference between the outer layer at 0 degree, 90 degree, or during the quasi-static test. These specimens were later tested in compression after impact test to measure the influence of the damage in the compressive behavior of this specimen. So here inside you can see the specimen, and you see the white line, which is the crack of the backside face. So these are typical plots of 3 plates. The red one is the intact, the plate that has not been submitted to impact. When we have low impact energy with only intralaminar crack, we have a decrease of the maximum force during the compression after impact test. But this decrease is more important when we have specimens that were heated at 8 joules. So these loading levels were normalized, so divided by the loads we had for the not tested specimen, and we can see that sorry, we can see that there is no significant influence of the damage in the resistance in compression of these plates up to 6 joules, but over 8 joules and 10 joules, we can see a decrease, which is not significant, but a decrease of the ability of the specimen to support the compressive loading. This result can be more significant depending on the size of the specimen that were tested in impact and also in the compression of the impact test. So the presence of pseudo thickness cracks were visible in these Flax epoxy composites. The equivalence between quasi-static and low velocity impacts was seen, and there is a compression of the impacts collapse limit is higher than the first visible cracks in the outer layer. This is the end of the presentation. So the issues I would like to highlight at the end of this presentation are that importance can be given to the testing and processing of natural fiber composites, the modeling, the variability, that is the scattering of their properties, and their robustness during in-service loading. Thank you for listening.